Good day everyone and welcome back to our Calculus 1 course. In our previous lesson, we introduced one of the most fundamental concepts in mathematics, that means functions. We learned what a function is, how a function assigns exactly one output to each input, how to evaluate functions, and how to determine the domain and range of a function. We also learned how to represent functions graphically, how to use the vertical line test to determine whether a graph represents a function, and finally we discussed several real-world applications of functions. Today, we will continue our study of functions by learning how we can combine two or more functions to create new functions. This idea is called operations on functions, and it is used throughout calculus, engineering, physics, computer science, economics, and many other fields. Suppose we have two functions, f of x and g of x. There are four basic operations that we can perform on these functions. The first and second operations are addition and subtraction. F plus or minus g of x equals f of x plus or minus g of x. In other words, to add or subtract two functions, we simply add or subtract their corresponding outputs. The third operation is multiplication. F times g of x equals f of x multiplied by g of x. Here, the value of the new function is obtained by multiplying the value of the two original functions. Finally, we have the division of functions. F divided by g of x equals f of x divided by g of x, provided that g of x is not equal to 0. Notice the important restriction here. Whenever we divide by a function, the denominator can never be 0. Therefore, before performing division, we must always check the value of g of x and exclude any value of x that makes g of x equal to 0. Now let us apply these definitions to a simple example. Suppose f of x equals x plus 2 and g of x equals x minus 1. First, let us find f plus g of x. Substituting the expressions for the two functions, we obtain x plus 2 plus x minus 1. Combining like terms gives 2x plus 1. Next, let us calculate f minus g of x. Substituting the two functions, we have x plus 2 minus x minus 1. Removing the parentheses carefully, we obtain x plus 2 minus x plus 1, which simplifies to 3. Now let us multiply two functions. We have x plus 2 multiplied by x minus 1. Expanding the product gives x squared plus x minus 2. Finally, let us divide the two functions. The quotient is x plus 2 divided by x minus 1. This fraction cannot be simplified further. However, notice that the denominator becomes 0 when x equals 1. Therefore, the domain of this equation includes every real number except x equals 1. This example illustrates an important point. Whenever we perform operations on functions, we are not only interested in obtaining the new formula, but we must also determine its domain. Ignoring domain restriction is one of the most common mistakes a student makes in calculus. Now that we understand how functions can be combined, let us become familiar with the most common types of functions that we will encounter throughout this calculus course. In fact, almost every problem in calculus involves one or more of these functions. Therefore, recognizing their equations and their graphs is an important skill for every mathematics, science, and engineering student. Let us begin with the linear function. A linear function has the general form f of x equals mx plus b. Here, m represents the slope of the line and b represents the y-intercept. The graph of a linear function is always a straight line. If the slope is positive, the line rises from left to right. If the slope is negative, the line falls from left to right. In other words, the slope tells us how rapidly the function changes. Linear functions are among the simplest mathematical models. For example, the cost of a taxi ride, a monthly utility bill, or the distance traveled at constant speed can often be represented by a linear function. Now, let us look at the quadratic function. A quadratic function has the general form f of x equals ax squared plus bx plus c, where a is not equal to 0. The graph of the quadratic function is called a parabola. If a is positive, the parabola opens upward. If a is negative, the parabola opens downward. Furthermore, every parabola has a special point called the vertex, which represents either the maximum value or minimum value of the function. Quadratic functions appear naturally whenever acceleration is involved. For example, the motion of a ball through into the air is described by a quadratic function. Anyway, let us continue with polynomial functions. A polynomial function is simply a sum of powers of x with non-negative integer exponent. For example, f of x equals x cubed minus 2x plus 5. Notice that the highest exponent in this example is 3. Therefore, this is called a third degree polynomial, or simply cube polynomial. Polynomial functions are smooth and continuous, and they play a central role in calculus. In fact, many complicated functions can be approximated by polynomials. This idea will become very important later when we study Taylor series. Now let us consider the rational function. A rational function is the quotient of two polynomial functions. For example, f of x equals x plus 1 divided by x minus 2. Notice that the denominator becomes 0 when x equals 2. Therefore, the function is not defined at x equals 2. As a result, the graph has a vertical asymptote at this value. In general, whenever you work with a rational function, you should always examine the determinator first. Finally, let us introduce the power function. A power function has the general form f of x equals x raised to the power n. Or more generally, f of x equals k multiplied by x raised to the power n, where k is a constant. For example, f of x equals x squared. F of x equals x cubed. Or f of x equals x raised to the power of 3 over 2. Depending on the value of the exponent, the graph may have very different shape. Some power functions increased very rapidly, while others grow much more slowly. Furthermore, power functions appear throughout mathematics and science. For example, the area of a circle depends on the square of its radius, while the volume of a sphere depends on the cube of its radius. These are examples of power model that we will study in more details later in this lesson. So, in this part of lesson, we became familiar with 5 important families of functions: linear functions, quadratic functions, polynomial functions, rational functions, and power functions. Each family has its own characteristic equations, its own graph, and its own applications. Recognizing this function at a glance will make many topics in calculus much easier to understand. Thank you for watching, and I look forward to seeing you in the next lesson of calculus.